Welcome to section 1.4. Today we're going to talk about the matrix equation AX equals B, and we're going to learn how to do that product. So let's start with the dot product. Many of you already know how to find the dot product between two vectors, but let's go through it anyway in case you don't know. In this class, we'll be dotting mainly a row vector with a column vector. And I've got it color-coded in this example here. What we're going to do is take the first entry of the row and multiply it by the first entry of the column. That's 1 times 3. And then we'll add that to the product of the second entries. 2 times 4, which is 8. Finally, we'll add that to the product of the third entries. 3 times 2. So 3 plus 8 plus 6 is 17. So we get a number. Let's do another one. This is going to be 5 times 2, which is 10, plus 4 times negative 3, which is negative 12, so we get negative 2. All right, we can use that definition of dot to define multiplication between a matrix and a vector. So if the rows of the matrix are R1 through Rm and the vector is X, what we're going to do is dot each row of A by X, and that will form each entry of the resulting vector. And here's how the dimensions work. If we take an m by n, so we've got m rows, n columns, and multiply it by a vector with n rows and 1 column, these two dimensions have to match. The inside dimensions have to match, they'll cross out, and what you'll get is a vector with m rows and 1 column. So here's a couple of examples. I've got the first one done out for us. We've got let's just check the dimensions first. We've got a 2 by 3, 2 rows, 3 columns, and we're multiplying by a 3 by 1, 3 rows, 1 column, and the result will be a 2 by 1. That's over here, 2 by 1. And so you can see what I did. I multiplied each entry of this first row times each entry of the column, and then I added my results. So you can read. I'm not going to read that all for you, but we get 15, 6 as our final vector. Let's do a couple more. Here I've got a 3 by 2, and I'm multiplying by a 2 by 1, so I should get a 3 by 1. So I'll get a vector with 3 entries. The first entry will be 1 times 2 plus 2 times 3. So I'll go slow. 1 times 2 is 2. 2 times 3 is 6. Second entry, I'm going to dot this row with 2, 3 to get negative 6 plus 12. And finally, if I take the last row and dot it with 2, 3, I get 2 times 0, which is 0, minus 3. Clean that up. We get 8, 6, negative 3. All right, and the last one is going to look a little different because our vector is x1, x2, x3, but this will be, if I dot, I'm going to get a vector with 2 entries. The top entry will be x1 plus 2x2 plus x3, and the second entry will be negative 3x1 plus 4x2 minus 2x3, and that's it. Here's just an easy application. If we look at this matrix has entries, the number of lattes that West Hills College sells on the first row, number of food items, and then the number of tea items. And the second row is the number of items that Hanford sells. And then we're going to multiply by the price vector 2, 5, 3. So 2 is the price of a latte, 5 is the price of a food item, and 3 is the price of a tea item. When you do that multiplication, you come up with the vector 95, 305. Well, what does that represent? The top entry represents the revenue in West Hills College Lemoore, and the second entry represents the revenue of Hanford. Revenue Hanford. And so if the prices were to change, you could just change up the price vector and do that multiplication again. Okay, the matrix equation AX equals B. In practice, the way you're going to do matrix multiplication, matrix times a vector, is exactly how I have it here, doing the dot product. But there is a theory behind it too that we're going to need. And the theory is written in this box here, and it says that the matrix product is a linear combination of the columns of A using the weights from the vector x. So, for example, let's just do this example out using the way we're going to do matrix multiplication in real life. So I'm just going to do the dot product. So if I take this matrix here and multiply by this vector, I'm going to get 4 plus 6 minus 7 on the top, and then I'll get 0 minus 15 plus 21. So that's going to be 3, 6. Now this step you can do mentally. You don't have to show me that step when you're doing matrix multiplication. After you do enough of these, you'll be able to do that in your head and go straight to 3, 6. Let me show you what the theorem says. The theorem says you would do this matrix multiplication as follows. You would take 4 times the first vector of A, 1, 0, and then add on 3 times the second vector of A, which is 2, negative 5. By the way, I meant column, the second column of A, and then 7 times the third column of A, which is negative 1, 3. All right, and then distribute the 4, distribute the 3, distribute the 7, add those 3 vectors together. I'll let you verify you indeed get 3, 6. So it's the same thing. You would never want to do that unless you were asked to do it. In general, we need this theory, but we're going to do matrix multiplication like this. And today we're only talking about a matrix times a vector, but pretty soon we'll be talking about a matrix times another matrix. And it will piggyback off of this definition. So let's look at the different notations we have at this point for linear systems. Here's a linear system right here. We know how to get the augmented matrix of that linear system. We just pull off the coefficients, and then this far right column is the answer column. And so that's another notation. We can write that as a matrix equation also. So this is the matrix equation for this linear system. And just to show you that explicitly, I'm going to multiply out this left side. If I multiply this vector times this matrix, I'm going to get x1 plus 2x2 minus x3. And then the second row will be 0 minus 5x2 plus 3x3. And that should be equal to the vector 4, 1. Okay, well, this gives actually 2 equations. This entry has to be equal to this entry, and this entry has to be equal to this entry. Well, that's exactly this linear system up here. They're the same thing. Let's look at the vector equation. If I take this x1 and distribute, so I'll get x1, 0, and then I'm going to distribute the x2, 2x2, negative 5x2, and then negative x3, 3x3 equals 4, 1. Again, reading along the top and reading along the bottom gives me these 2 equations for my original linear system. So I suggest you pause the video and write this guy, this linear system, as a vector equation and as a matrix equation. Okay, hopefully you did that. Let's do the matrix equation first. That's easier. Matrix equation, I'm going to write down the coefficients. 1, 1, negative 3, 0, 10, 2. And I'll multiply by the vector x1, x2, x3. And that should be equal to 1, 0. There's my matrix equation. All right, let's do the vector equation. The vector equation would be x1 times the vector. Look at the coefficients of x1. They're 1 and 0. Plus x2, look at the coefficients of x2. They're 1 and 10. And then x3, we've got negative 3 and 2. And that should be equal to 1, 0. Okay, now let's talk about some theorems involving AX equals B. This first theorem is pretty straightforward. It tells us, first of all, that the solution set to this matrix equation is equivalent to the solution set to this vector equation. So they're equivalent because they're the same thing. One's just written in vector form and the other is a matrix equation, but they're the same linear system. And then the equivalence between 2 and 3 we saw last time. And so the upshot of the equivalence between 2 and 3 is in blue here. AX equals B is consistent if and only if, that's the double arrow, B is a linear combination of the columns of A. So let's use that in example 3 here from your book, and I've glossed through most of it. We're given a matrix A, and we're given a generic vector B, and we want to know, is AX equals B consistent for all B? And so what they do, if you read your book, they reduce the augmented matrix A augmented with B, and I did that, and I come down to this final matrix here, and I see that I've got all zeros in the A part, and then this entry in the answer column. So we know that this will only be consistent, this is going to be consistent if and only if this entry over here is 0, because you can't have a 0 equal something non-zero. So we need B3 minus 2B2 minus 2B1 equal to 0. Okay, now for the big theorem. This is Theorem 4, and this is definitely a memorize this theorem. So A is an m by n matrix. The following are equivalent. AX equals B is consistent for all B. B is a linear combination of the columns of A for all B in Rm. That's what that backwards E means, in Rm. Well, that's the definition of span. Rm is spanned by the columns of A, because every vector in Rm can be written as a linear combination of the columns of A. And finally, A has a pivot in every row. Now, why is that important? That's illustrated by example 3 above. If A doesn't have a pivot in every row, so up here, if we look up to example 3, let me erase some of this, A did not have a pivot in every row. This last row had no pivot. Well, that caused a problem in terms of consistency, because if this expression here was not 0, then we would get a non-consistent system. Well, that can't happen if A has a pivot in every row. So if this had been a 1 here, or any other number, non-zero, then this system would have been consistent for all B. Okay, and then finally, linearity. The Theorem 5 says that matrix multiplication is linear. What does that mean? It means if we take A times the vector U plus V, that's the same as AU plus AV. So we can distribute over a plus sign. And then this one says we can take scalars and pull them out of matrix multiplication. So it sounds simple, but let me just show you what it means in practice. So here's a actual example. Here's a matrix A and the sum of two vectors. Okay, and so what I'm saying, the theorem says that if we take the left-hand side of this equation up here would be 1, 2, 0, negative 5, whoops, and you're multiplying by, you're going to add those two vectors, 6, 8, okay? If you do that multiplication, you should verify that you're going to get 22, negative 40. Well, that's the same as if you take A and multiply by U, which is 4, 7, take A and multiply by V, and then add those two vectors together. So I'll let you verify that the right-hand side, if you take A and multiply by U, you'll get, I believe, 18, negative 35. And if you take A and multiply by V, you get 4, negative 5. Add those together, and you get 22, negative 40. Okay, and I'll let you just verify that you can either multiply this negative 3 by this vector and multiply by the matrix A, or you can take A, multiply by the vector, and then multiply every entry by negative 3. Doesn't matter. Okay, and that's the end of this section.